presented by Caltech.
Welcome. My name's Jed Buchwald. I'm a historian of physics here at Caltech, and I'm very pleased to welcome you to the 6th Biennial Bacon Lecture. The Bacon Foundation is a wonderful group of people who have been funding this for the last 10 years and are continuing to do so. It's a prize that we offer every 2 years here at Caltech to the best historian of science that we know about in the world. We bring them here, they fund a conference, and they give a wonderful talk. This year, of course, is particularly propitious because we are going to be hearing about the early history of general relativity and the very moment in time in which LIGO has been all over the news and Caltech's name is across the world. Our speaker today is Jürgen Renn. Jürgen is one of the two founding co-directors of the Max Planck Institute for the History of Science in Berlin. He has a broad spectrum of work that he's engaged in over the years. He took his PhD in mathematical physics at the Technische Universität in Berlin and moved on rapidly after that into the history of physics. His earliest work was on preclassical mechanics, Galileo, did some foundational work in understanding where Galileo's early experimental discoveries came from. And in more recent years, he's been working on the history of general relativity with the groups that he's founded at the Max Planck Institute. I think it's fair to say that the Institute in Berlin is now the epicenter of major work in the history of modern physics, and not only in that, but in other areas as well. Jürgen has written also about the history of statistical mechanics, quantum mechanics, and in other areas much more broad than that. He's actually written material on the new idea of the Anthropocene era, the formation of the world and the Earth as it stands today as a result of human activities. But today we're going to hear about the work that he's done over the years on the history of general relativity. He's published a number of major works on that subject, which I think will certainly stand the test of time over the coming decades. And he has a lot to tell us, so with that, I'll turn it over to Jürgen.
Dear Jed, dear colleagues from Caltech, dear colleagues who came from the outside, it's an honor and a pleasure for me to speak to you tonight. It's a great moment, a historical moment after the discovery of gravitational waves predicted by Einstein 100 years ago. Of course, we are wondering how Einstein himself would have reacted to this discovery. So this is Einstein, I hope at least, enjoying his time with LIGO. But we as historians are, of course, interested in how it all began. And of course, it began with special relativity. Special relativity emerged from the clash of two principles. One of it was the principle of relativity that Einstein tried to extend from mechanics to all of physics. And the other principle was that of the constancy of the speed of light. And the attempt to reconcile those two principles led to a major conceptual revolution. It forced Einstein to introduce a new framework of space and time, and it also implied what is probably the most famous formula of physics, expressing the relation between energy and mass. Now, what does all of that, by the way, this was all done at the Patent Office in Bern in 1905. What does this imply for the phenomenon of gravitation, the new framework of space and time? So Einstein, in 1907, was sitting down to write a review article in which he reviewed all the phenomena of physics in order to see what had to be done in order to adapt them to the new framework of space and time established by special relativity. It was a routine task. And dealing with gravitation in that context was also a routine task, or so it seemed in the beginning. But then Einstein had to deal with a principle that was already established by Galileo hundreds of years ago, namely what is today called the universality of free fall, the fact that all bodies fall with the same acceleration. How can these two requests be reconciled? The Galileo principle is based on the equality of gravitational and inertial mass, and core to the framework of special relativity is the relativity of simultaneity. Can these two principles be reconciled? And thinking about this in the framework of writing this review article brought Einstein not to the most famous formula of physics that he had already done, but to what he later called the happiest thought of my life. And in the first part of this lecture, I will trace the origin of this happiest thought of his life. Again, as I said, this was still done at the patent office in Bern. So let us now do one of these famous thought experiments that Einstein loved. And actually, that is the thought experiment that Einstein performed in the context of the considerations I've just been describing. So when two people, one on a moving train and one standing on a platform, each drop a stone, will the two stones hit the ground simultaneously? According to classical physics, to Newtonian physics, yes, but according to special relativity, no. That is surprising. Was there any way to impose the universality of free fall and to maintain Galileo's principle? This is what inspired Einstein. Later he recalled, and I'm quoting him, "Then came to me the happiest thought of my life in the following form. In an example worth considering, the gravitational field only has a relative existence in a manner similar to the electric field generated by electromagnetic induction. Because for an observer in free fall from the roof of a house, there is during the fall, at least in his immediate vicinity, no gravitational field." Now the great thing is that this allowed Einstein to simulate now gravity by acceleration. And he could now treat accelerated frames of reference with the help of special relativity, so he had a handle on dealing with gravitation in the framework of special relativity, but in a new way that preserved the universality of free fall. He could, for instance, predict that light will be bent in a gravitational field. So let me give you some historical background. Where did these revolutionary ideas come from? They came, as I have tried to emphasize, from conceptual conflicts. More precisely, they originated at the borderlines of different domains of knowledge where different conceptual systems clashed with each other. Let us take a look back at Einstein's miracle year, 1905. All of Einstein's great 1905 papers emerged from problems at the borderlines between established disciplines. For instance, his paper on Brownian motion emerged from a borderline problem between mechanics and thermodynamics. His paper on the light quantum, one of the origins of the later quantum theory, emerged from a borderline problem between thermodynamics and electrodynamics, namely Planck's problem of the thermal stability of radiation. And finally, his paper on the electrodynamics of moving bodies, that was the title of Einstein's 1905 paper, gave rise to special relativity. After special relativity had been established, a new borderline problem emerged. It was the challenge to create a relativistic field theory of gravity. So far for the borderline problems. The point is, we can identify them in hindsight, but not everybody saw these as conflicts. Why did Einstein see them as conflict? What was his special perspective? And let me focus now on the problem of gravitation again. In his later popular book on the special and general theory of relativity, Einstein stated, "Since the introduction of the special principle of relativity has been justified, every intellect which strives after generalization must feel the temptation to venture the step towards the general principle of relativity, extending the principle of relativity to accelerated motion." As a matter of fact, however, Einstein was practically the only intellect who saw this need. So, where did the idea of a generalization of the relativity principle actually come from? Now, Einstein was an avid reader of philosophical literature and particularly fascinated by Mach's historical critical analysis of mechanics. What could Einstein learn from Mach? Mach had reconsidered Newton's bucket experiment. Why does the water rise when it starts rotating? Newton's answer was because it moves with respect to space, absolute space. Mach's answer was different. He claimed that it moves because it moves with respect to the fixed stars. That would make it a relative motion, an interaction, an inertia, an interaction between bodies in relative motion with respect to each other, the water and the stars. In other words, would Einstein's head fly away if there were no fixed stars that are responsible for this interaction? So let us take another look at what I have called here the happiest thought of Einstein's life, or what he has called the happiest thought of his life, and identify another element that was relevant here besides the influence of Mach's critique of mechanics. So when we read this, the gravitational field only has a relative existence in a manner similar to the electric field generated by electromagnetic induction, we can see that it was the analogy of the gravitational field theory with the well-known theory of the electromagnetic field, on which Einstein, of course, was a specialist, that inspired him to this happiest thought as well, alongside the influence of Mach. Now, with the help of Mach, Einstein was in the position to complete the analogy between electromagnetic theory on the one hand and gravitational theory on the other hand by conceiving gravitation and inertia together as corresponding to the electromagnetic field. And as you will see, this analogy will guide him all these years from 1907 to 1915 to the completion of general relativity. It was a very important analogy for Einstein. So now the borderline problem of a relativistic field theory is becoming more specific. It has to incorporate insights such as the relation between gravitation and inertia, and also the basic principles of field theory. That is what laid out Einstein's path to general relativity. So let me briefly recapitulate. Which questions did we answer so far? What motivated Einstein to launch the search for general relativity? I have claimed it was an unexpected obstacle on the road to adapt all of physics to the new framework of special relativity that brought him to question the space-time framework that he had established just 2 years ago. But then there is a second question. How could Einstein have known where to go? He certainly had no empirical clues. Light bending, redshift, the expanding universe, gravitational lensing, black holes, gravitational waves, all of that came later, and some of it much later. What was crucial was that Einstein had a clever way of transforming the existing knowledge of classical physics in order to suit his heuristics. By comparison, the famous problem of the perihelion motion of Mercury was a relatively minor issue. Nevertheless, as it was the only empirical hint, let us take a closer look at that phenomenon. The slight rotation, I've exaggerated it here a little bit, was known since the 19th century, and it was the only deviation from Newton's theory that Einstein could use to probe his new theory. It was a small effect, and even of that small effect, most of it was explained by Newton's theory of the solar system, the slight rotation of the orbit of Mercury. It was influenced by the other planets, but there was a small difference of 43 arc seconds that remained unexplained. Already in 1907, Einstein expected that the new theory will explain this anomaly. Just as he had predicted light bending and gravitational redshift, all of that, the famous 3 classical tests of general relativity, were predicted already in 1907. So 1907 was an important milestone, but let us get a little overview over the further milestone. So the next milestone is Prague and then Zurich in 1912, where Einstein found that gravitation is related to space-time geometry and where he introduced the metric tensor for describing it. And then in 1915, he found the gravitational field equation. And usually this is portrayed as a drama in 3 acts. The problem, however, is that this portrait, this drama here, leaves out the villain in the story, or what is usually considered the villain, namely a theory on which Einstein worked between 1913 and 1915, in Zurich mostly, later also in Berlin, and that he discarded. It's called the preliminary or the draft, and in German, the Entwurf theory. Now the point is what for other accounts is the villain of the story, the theory that was discarded, in my account, by my book, is the actual hero, as we shall see. But let us proceed in order. In the beginning of 1911, Einstein became the chair of physics at the German University in Prague, his first full professorship. We have a later testimony from Otto Stern about Einstein in his office. I expected to meet a very learned scholar with a large beard, but found nobody of that kind. Instead, sitting behind a desk was a guy without a tie who looked like an Italian roadmender. This was Einstein. He was terribly nice. In the afternoon, he was wearing a suit and was shaven. I hardly recognized him. So this is Einstein, Prague, and this is the Physics Institute where he worked. But for our purpose, more important is a notebook that has been preserved. All of Einstein's materials are held by the Hebrew University at the Einstein archives. They're edited here at Caltech by the Einstein papers. And so we have these treasures that allow us to reconstruct Einstein's pathway. And here is a notebook from Einstein's time in Prague. And there are some simple expressions when he started to work out the theory of gravitation. They're still a far cry from the later complex equations of general relativity, but they do have the same structure. There's a field equation, and there's an equation of motion. So these are 2 important concepts. Let me briefly explain. A field equation is when matter tells the field how to behave. And an equation of motion is when the field tells matter how to move. And that structure, of course, was modeled after electromagnetic field theory. So what did Einstein achieve in 1912? So we have talked about the achievements in 1907. Now we are at the achievements of 1912. He knew that the field had to be a combination of gravitation and inertia. But he did not know how to represent it mathematically. Fortunately, the problem could be sliced up. It had 2 parts, as we have just seen. And he first tried to solve the problem of the equation of motion. And in particular, the simple case, how does a body move when no other forces, other than gravitation and inertia, act on it? Again, the analogy with electromagnetism came to his rescue. It made sense at other special cases of dynamic gravitational fields, such as the forces acting in a rotating frame of reference. By Einstein's book, it should be possible to consider such a system at rest and the forces acting, the centrifugal forces acting there, as dynamic gravitational forces. This is what he took from Mach, as I have tried to explain. So, but the clue is the combination of gravity and inertia. So what could he learn now? Let us look at a rotating disk and try to measure its circumference with little rods. So let me set this into motion here. And because of the length contraction predicted by special relativity, the rods will be shrunk, so then one needs more of them to cover the circumference. In other words, this ratio between the circumference and the diameter will be larger than pi. This simple thought experiment gave Einstein the idea that to describe gravitational fields, general gravitational fields, dynamic gravitational fields, one needs to go beyond Euclidean geometry. Now, non-Euclidean geometries were well known. Einstein himself wasn't too familiar with them. He had some courses, he had skipped some courses at the ETH, but he did know that a straight line in such a geometry corresponds to a straight test line or a geodesic, like here in the picture, the grand circles on a sphere. That solved for him at the same time the problem of the equation of motion, because when no other forces act in such a geometry, a particle will just follow the straightest possible line. Now, the program of the new theory was clear. As Einstein later stated, the so-called attraction of gravitation is, according to our present knowledge, a state of space, which is caused by masses and which acts upon masses. John Wheeler put that even more succinctly: matter tells space how to curve, and curved spacetime tells matter how to move. These are quotations from a much later time, but Einstein could have stated them already in Prague, 1912. That is a lot what he achieved in Prague, but that was not all. He achieved something else. He calculated the effect of gravitational lensing, that is the focusing of light by gravitation, an effect that he published only 24 years later. It gives rise to these beautiful and useful astronomical objects that are now called Einsteins Rings. They are useful because they act like lenses in the universe. They make us see farther than we would be able without them. And Einstein discovered them in the connection with an observation of a nova star around 1912, but he came to the conclusion he couldn't explain that with gravitational lenses, so he left the calculation. But more importantly for him, during this period, he got in touch with Erwin Freundlich, the first astronomer who took Einstein's prediction seriously. He wrote to him, "I would be delighted if you wish to tackle this interesting question," referring generally to light bending. "I know perfectly well that to answer it through experiments is no easy matter," and it was no easy matter. So, but back to our story. In the summer of 1912, Einstein returned to Zurich. He knew that he could describe a curved spacetime by the metric tensor. The metric tensor is a complicated object. It replaces the one Newtonian gravitational potential with 10 gravitational potentials. As I have just said, Einstein could even write down an equation of motions using the metric tensor that he achieved relatively quickly, but he had no clue as to how to find a field equation for this complicated object, for these 10 gravitational potentials. Now, one of the most important sources for our story is a notebook in which Einstein entered his calculations in the winter of 1912-1913, the so-called Zurich notebook. Einstein's first attempt to deal with the mathematics of the metric tensor look rather pedestrian. This is one of the first pages dealing with gravitation in that notebook. He tried to bring together the metric tensor with what he knew about a gravitational field equation at that point, which was also relatively little. Now, how did Einstein actually found his field equation? That has been a subject for many years. It took Einstein 8 years, and it took this team of 5 scholars more than 10 years to redo, to decipher, and to reconstruct all of his calculations. So not quite as efficient as Einstein himself. But Einstein had difficulties too. And he also was not alone. When he became desperate because of the mathematical challenges, he called his old friend Marcel Grossman for help. Grossman had helped Einstein to survive his exams and gotten him his job at the patent office. Now he helped him master the problem of gravitation. Einstein wrote to Arnold Sommerfeld, and I quote, "I'm now working exclusively on the gravitation problem and believe that I can overcome all difficulties with the help of a mathematician friend of mine here. But one thing is certain, never before in my life have I toiled anywhere near as much, and I have gained enormous respect for mathematics, whose more subtle parts I considered until now in my ignorance as pure luxury. Compared to this problem, the original theory of relativity is child's play." Indeed, one immediately recognizes Grossman's intervention in the notebook. His name appears next to the Riemann tensor, the crucial object for building a relativistic gravitational field equation. Einstein immediately used it to form what he considered a candidate for the left-hand side of the field equation. But it turned out to be difficult to reconcile Einstein's physical expectations with the new formalism. Groping in the dark, Einstein and Grossman hit upon the essentially correct field equations in the winter of 1912-1913, that is, 3 years before the final publication. Here they are in a weak field limit. But Einstein and Grossman found that these field equations do not match their physical expectations. Eventually, they had to learn how to adapt these expectations, their physical expectations, to the implications of the new formalism. And that is really a crucial point. We are talking here really not just about a dramatic history of a discovery, we are talking about a learning experience that took place between a mathematical formalism and new physical concepts that were being shaped during the process. So, as this is so deeply important, I have permitted myself to use a metaphor to explain you the mechanism behind a field equation. It's relatively simple. Einstein started out with a handmade mathematical formalism, at least before Grossman came into the game. But it did the job, extracting from the source of the field, mass and energy, the gravitational field. That's what a field equation is all about. Of course, it was most crucial that the familiar special case of Newtonian gravity would also come out under appropriate circumstances. And Einstein had to make sure that this machine was firmly grounded in basic physical principles, and in particular, in the conservation of energy and momentum. And you can see this is a sturdy machine, firmly anchored. But he also wanted to generalize the principle of relativity to accelerated motions, as we have seen, and hence he looked for a machine that worked in more general coordinate systems. But at that point, he didn't know quite in which. The latter point was one that was rather unclear to Einstein effectively, but with Grossman came the dream of a much more sophisticated machine, a machine that worked for all coordinate systems because it was generally covariant, a very slick machine. So here the starting point was a sophisticated mathematical formalism based on the Riemann tensor. And then the machine, of course, had to work in the same way. A source makes a field, but does the Newtonian limit come out right? And is the machine firmly grounded in the principles of energy and momentum conservation? It certainly doesn't look quite that way. In any case, it was generally covariant, working in all coordinate systems. The problem was that it was not entirely clear whether that machine actually would deliver the requested physical results, and what kind of tweaking it would take to get them. In short, the mechanism was great, but the output uncertain. Given this situation, Einstein could now pursue two different strategies. Physical strategy, which suggested to start with an object that fulfills the physical requirements and then check to which extent it actually generalizes the relativity principle. And a mathematical strategy that suggested to begin with an expression that holds in all coordinate systems and then check whether the physical requirements, the Newtonian limit, and the energy momentum conservations are also fulfilled. In the winter of 1912-1913, Einstein and with him Grossman constantly oscillated between these two strategies. At the end of the winter, he decided for one of them, the physical strategy. Well, not quite, but rather a physical strategy tweaked and adapted to match the requirements of a general relativity principle, of energy momentum conservation, and so on. So it was a homemade extension of the original machinery. Actually, the exploration of all the details was an important part of Einstein's learning experience that I have mentioned before. Now, from the metaphor back to the sources. The result of the collaboration between Einstein and Grossman in the winter of 1912-1913 was a hybrid theory, the so-called Entwurf or draft theory, the villain or hero that I have mentioned before. Why was it a hybrid theory? It was a hybrid theory because the equations of motion were generally covariant, retaining their form in all coordinate systems. But the field equation was not. It was not generally covariant. It was not even clear under which coordinate systems it would be covariant. Nevertheless, Einstein was quite proud. To his new love and future second wife, Elsa, he wrote, "I finally solved the problem a few weeks ago." I solved the problem, he wrote. "It is a bold extension of the theory of relativity together with the theory of gravitation. Now I must give myself some rest, otherwise I will go kaput." But was it actually worth the effort? Wasn't the Entwurf theory rather just a blind alley and a waste of time for more than 2.5 years? As I said, most standard accounts say yes, and speak of a comedy of errors. This is how Einstein himself looked back on the genesis of general relativity, from a later recollection. "I have learned something else from the theory of gravitation. No collection of empirical facts, no matter how comprehensive, can ever lead to the formulation of such complicated equations. They can only be found through the discovery of a logically simple mathematical condition that completely or almost completely determines the equations. Once one has those sufficiently strong formal conditions, one requires only little knowledge of facts to set up a theory." This sounds indeed like the Entwurf theory based on the physical strategy that is on, empirical facts, had just been a blind alley, eventually giving way to a switch to the much more elegant mathematical strategy. So far, Einstein's recollection. But Einstein's recollection was colored by his own later experiences, struggling to find unified field theory, and it is actually misleading, because the preponderance of contemporary evidence from the period 1913 to 1915 militates against the idea that it was a return to the mathematical strategy in the 11th hour that prepared the way to general relativity. Einstein himself warned, "If you want to find out anything from the theoretical physicists about the methods they use, I advise you to closely stick to one principle. Don't listen to their words. Fix your attention on their deeds." But if this is so, and if the Entwurf theory was important, what was its role? What function did it have for the creation of general relativity if it turned out to be a wrong theory in the end? To answer that question, let me use another metaphor. The Entwurf theory worked as a scaffolding for building an arch or a bridge between physics and mathematics. Here is the scaffolding. It's a metaphor that was introduced by Michael Janssen, with whom much of this work was done. Here it is interpreted, I interpret it, as preparing the building of a bridge between physics and mathematics. On its basis, Einstein first calculated the Mercury Perihelion motion, as we shall see, and working out its mathematical structure, and by its it means of the Entwurf theory, of that preliminary draft theory, Einstein worked out its mathematical structure and set up a variational formalism for it. Now, the Mercury calculation eventually helped him to solve the problem of the Newtonian limit. And the variational formalism helped him to solve the other problem he had encountered with the mathematical strategy, that is the conservation of energy and momentum. Now, this prepared the situation of November 1915, when it eventually came to a situation in which the scaffolding was torn down. So, let us look at the first issue, the issue of the Mercury Perihelion motion. It's a problem that was studied in detail by Michel. In 1913, Einstein, together with Michele Besso, calculated the Mercury perihelion motion on the basis of the Entwurf theory, and the value which they first miscalculated came out too small. This did not shatter, however, Einstein's confidence in the theory. He never mentioned the result, but reused the method developed under the auspices of the Entwurf theory in November 1915, when it actually helped him to understand the problem of the Newtonian limit. So here is the manuscript with some of Einstein's calculation. It's one of the fascinating manuscripts that were analyzed in the context of all of this work with a calculational error by Einstein. You can see it, I think, still, Diana, in the Einstein exhibition that the collected papers show at their offices and will be at the Huntington, right? It is now at the Huntington Library. So the creation, one other thing that you can learn from all of this is that the creation of general relativity was actually to a surprising extent a team effort. Here are the names of some of Einstein's helpers and competitors: Freundlich, Grossman, Besso, Bernays, Fokker, Abraham, Nordstrom, Kotler, me, Hilbert. I will not explain. There is a story behind each of these names. But you may wonder, some names are missing. What about the Berlin physicist that lured Einstein to come to Berlin in 1914? Here is what Einstein wrote to his friend Michele Besso. The fraternity of physicists behaves rather passively with respect to my gravitation paper. Lauer is not open to the fundamental considerations, and neither is Planck, while Sommerfeld is more likely to be so. A free, unprejudiced look is not at all characteristic of the adult Germans, blinders. And here is an artist's impression of Einstein's situation in 1914 when he moved to Berlin. This is actually due to Laurent Taudin, who did most of these drawings. Berlin's physics elite, Haber, Nernst, Rubens, Planck, and Einstein's old and new family are watching as Einstein is pursuing his new theory of gravity and his idée fixe of generalizing the relativity principle, while carried by giants of both physics and mathematics, Newton, Maxwell, Gauss, Riemann, and scientists of lesser stature, Grossman, Nordstrom, Freundlich, and Besso. The Mercury calculation of 1913 really did act as a scaffolding for what Einstein achieved in November 1915, when he redid this calculation, now on the basis of the correct theory. His colleagues were amazed how quickly he could calculate. The famous mathematician David Hilbert wrote him a postcard just a day after Einstein had submitted the paper. "Congratulations on conquering the perihelion motion. If I could calculate as fast as you can, the electron would be forced to surrender to my equations, and the hydrogen atom would have to bring a note from home to be excused for not radiating." All Einstein had to do was to redo the calculations for the perihelion motion in the Entwurf theory that he had done with Besso in 1913, but never published. Einstein didn't bother to tell Hilbert about his earlier work. Apparently, he wanted to give Hilbert a dose of his own medicine, seeing Hilbert as somebody who gave the impression of being superhuman by obfuscating his methods. So much for the role of Besso and the perihelion calculation in building a scaffolding for the transition to the final theory. In November 1915, it helped Einstein to overcome his earlier problems with extracting the Newtonian limit from a field equation found along the mathematical strategy. But what about the second problem, the conservation laws? Again, the Entwurf theory served as a scaffolding. In 1914, Einstein and Grossman set up a variation of formalism for the Entwurf theory from which it was easy to derive the conservation laws, actually anticipating Noether's famous theorems. That formalism was general enough to allow the derivation of the conservation laws also for other theories, including the ones that Einstein had discarded in the winter of 1912-1913. Now, what is a variation of formalism? I look at the watch and I have thought long and hard about how to explain a variational formalism without mathematics. And here is what I have come up with. The variational formalism is a machine that can make machines. You can use it to make a candidate field equation for the physical strategy. Or you can change the settings, and you get a different machine. For instance, a candidate field equation for the mathematical strategy. Having constructed such a formalism is what allowed Einstein to switch from the Entwurf theory to the theory he presented on November 4th, 1915. But let us now finally turn to what happened in Berlin. Who is the woman waiting here? Is Einstein's new love and future second wife, Elsa, an important reason beyond the attractive academy position why he accepted the offer from Berlin in the first place? But back to general relativity. As we have just seen, Einstein had resolved his two major problems that had prevented him in Zurich to accept candidate field equations found along the mathematical strategy, namely the requirement to get out the Newtonian special case and the conservation laws. That confronts us with a puzzle. Why did Einstein not go back to the mathematical strategy right away, once he had resolved these problems by the end of 1914? It was a matter of perspective. He firmly believed in the Entwurf theory and had concocted all kinds of arguments in its favor. For instance, the whole argument. And those of you who have studied this will find that the whole argument is a whole in my presentation, but I just didn't have time for it. I will come shortly back to it a little bit later. But it was an argument strongly in favor of the Entwurf theory. But by October 1915, his perspective was gradually changing because problems with the Entwurf theory were accumulating. It did not explain the perihelion problem. Well, we have seen that Einstein could live with it. He just, put it under the rug, didn't mention it in his publications. It did not allow him to conceive rotation as rest. That was a major blow, considering his Machian ambition. And it did not follow uniquely, as he had hoped, from the variational formalism that he had set up. But this failure was actually a blessing. I forgot to keep track here. This failure was actually a blessing in disguise. It meant that the formalism was actually more general and not just tailor-made for the Entwurf theory. So he could use it. So these problems were the prelude to the drama of November 1915, when Einstein published, week after week, his 4 conclusive publications on general relativity. On the 4th of November, that's the transition from the Entwurf theory to the new mathematical objects, with an addendum on the 11th of November, the Mercury paper on the 18th of November, and the final field equations on the 25th. The first paper contains an interesting hint at what Einstein considered the fatal prejudice that had hindered him so far, and also what was the key to the solution. The subsequent papers successively straighten out the logical structure of the theory, show that now the Mercury problem works, and show that the logical structure of the final theory is flawless. In order to understand what the fatal prejudice was and what the key to the solution was, we have to once more take a closer look into the mechanisms at work here. There is indeed not just the source in the field. There is also the gravitational potential represented by the metric tensor and its connection with the gravitational field. That connection is expressed by a differential operator. One way to express this differential operator turned out to be a fatal prejudice. The other, the key to the solution. As it turned out, it was essentially sufficient to change one element in the variational formalism developed for the Entwurf field equations in order to get the theory from November 4th, namely redefine the gravitational field. There are smoking guns for this reconstruction of how Einstein found the field equations in 1915. Here are 2 ways in which Einstein expressed the connection between the field and the potential. One in the 1913 Entwurf theory and the other in the theory of November 4th. In the paper himself, he speaks, as I have mentioned, of the first way as a fatal prejudice, And in a later letter to Sommerfeld, he characterized the second option as the key to the solution. In the end, the transition from the in-Wurf theory, based on the physical strategy, to the November 1915 theory, based on the sophisticated math of the Riemann tensor, seems to have been a rather simple step. But what made this step possible was the scaffolding represented by the variation of formalism Einstein had built for the in-Wurf theory. Remember what a variation of formalism is? Yes, it's a machine for making machines. It made it simple to pass from a machine based on the fatal prejudice to a machine that represented the key to the solution. It actually was a dramatic process. I have simplified here, because Einstein had to revise the architecture of his theory step by step, and that is what happened in the final 4 publications of November 1915. To Sommerfeld he wrote, "Unfortunately, I have immortalized my final errors in the Academy papers." And to his friend Ehrenfest he wrote, "It is convenient with that fellow Einstein. Every year he retracts what he wrote the year before." In Einstein's defense, one has to remember what contributed to the drama was that the mathematician David Hilbert was, or at least seemed to be, hot on his trail. Hilbert presented his field equations in Göttingen on November 20th, that is 5 days before Einstein. He used the Riemann curvature scalar in his variation of formalism. He did not explicitly write down the field equation, but he could have easily calculated it, of course. The late 1990s, page proofs of Hilbert's paper, which itself was not published until March 1916, turned up. These page proofs carry a date stamp of December 6, 1915. So, after Einstein's publication. So did Hilbert beat Einstein to the punch? His page proofs show that the original version of Hilbert's theory was conceptually closer to the in-Wurf theory than to Einstein's final version. Hilbert's theory of December 6 was, just as the in-Wurf theory, a hybrid theory with extra conditions on the admissible coordinate systems. This restriction of coordinates was later dropped in the published version appearing in March 1916. Hence, the moral is, Einstein could have taken his time in November 1915 and need not have worried about Hilbert stealing his thunder. Hilbert did not build a bridge between mathematics and physics as Einstein had done. In fact, he didn't worry about these problems of the Newtonian limit and energy momentum conservation in the way that Einstein had done. So on November 25, 1915, the edifice of general relativity seems complete. Is this the end of the story? No, it was not even the end of the beginning. The theory which Einstein had built between 1907 and 1915 has since stood the test of time. But what about its interpretation and its further elaboration? In particular, what remained of Einstein's original motivations and ambitions? What, for instance, became of the whole argument supporting the in-Wurf theory by arguing that a generally covariant theory would be problematic? What became of the idea of extending the relativity principle from uniform to arbitrary motions by imposing general covariance? What became of the idea of Mach to explain all inertial effects by an interaction of material bodies? The theory that Einstein had created was different from what he had expected. It had introduced a new language for describing nature that now the scientific community was trying to master. Einstein had to learn it as well. These were the formative years of general relativity, which I'm currently investigating with Hannah Gutfreund. A scientific community emerged around general relativity. The first exact solutions were found. Fundamental concepts underlying the theory were being revisited. New insights were gained into the relation between the mathematical formalism and the physical interpretation, so continuing the dynamics I have explained to you for the Zurich notebook. First attempts were made at confirming predictions of the theory. The confirmation of light bending during a solar eclipse in 1919 turned Einstein into an international star. Relativistic cosmology emerged. The cosmological constant was introduced and withdrawn. Each of these lines is a drama by itself. Attempts were made to go beyond general relativity. It took a long time before the physics community accepted that general relativity was such a stable, such a sturdy theory as we now see it. People initially tried to quickly go beyond it, creating something like unified field theories of gravitation and electromagnetism. And Einstein did so for the rest of his life. And last but not least, gravitational waves were predicted. The first 15 years of general relativity were a vibrant time. And let me give you just one example. How did gravitational waves emerge during the genesis of general relativity, and how did the theme evolve during its formative years? This can be, of course, only a short comment, and for the whole story, I refer you to the magnificent book by Dan Kennefic. The idea emerged, of course, in comparison with electromagnetic field theory, given the close analogy that I have stressed here. Several people had thought about gravitational waves. One of the first was Max Abraham, as early as 1912. But Einstein compared his theory of gravitation to a racehorse missing 3 legs, so he apparently didn't take it so seriously. And Einstein himself, as early as 1913, apparently had thought of gravitational waves. In a discussion following his lecture in Vienna, Max Born asked him how fast the effects of gravitation propagate according to the Entwurf theory. And Einstein responded, "It is extraordinarily simple to write down the equations for the case in which the disturbances one places into the field are infinitesimal." Unfortunately, we don't have any more details. We just see once more that the Entwurf theory acted as a scaffolding. Let me now come to the formative years. After the completion of general relativity, the situation changed, and the issue of gravitational waves demanded more serious attention. The first to bring it up was the astrophysicist Karl Schwarzschild. Karl Schwarzschild was an important person in the early history of general relativity. He was the first to formulate exact solutions. Unfortunately, he died in May 1916, much too early. The story would have been different with him. But he played a role in the emergence of the theme of gravitational waves. He raised the question of the existence of these waves in letters that he wrote to several people, including Einstein and Sommerfeld. To Sommerfeld, he wrote, "I'm rummaging around further in Einstein's field equations." He was at the Eastern Front at the time, and he was busying his mind with these calculations, rummaging around in Einstein's field equation. Today, he wrote, "I'm totally flabbergasted. Setting up the problem of the plane gravitational wave according to Einstein, one obtains," and then he writes down a differential equation, "hence no wave motion, but infinite speed of propagation." So there was apparently a clash between what he expected intuitively, namely the existence of such gravitational waves, and his calculations. Einstein checked the calculation and response, thus there are no gravitational waves analogous to light waves. But the problem remained open until another astronomer entered the scene. He was, like Schwarzschild, one of the early pioneers in applying general relativity to the universe, the Dutch astronomer Willem de Sitter. After Schwarzschild's letter, Einstein had come to believe that gravitational waves do not exist because the approximation method used by Schwarzschild was not legitimate in the final theory. But after what he had learned from de Sitter, he rushed to return to the challenge of gravitational waves, and the advice he got from de Sitter helped him to overcome the hurdle that he found in Schwarzschild treatments. And on the 22nd of June 1916, Einstein submitted his first paper on gravitational waves. So the story was still not over, however, and it gained new momentum when another player entered the scene, the Finnish physicist Cunha Nordstrom. So you see a bit of the dynamics of the formative years when people enter the discussion and also dare to challenge Einstein's interpretation of general relativity. And Nordstrom's intervention led to a revision of Einstein's original calculations, and the revision was published in 1918, and I just quote a few lines from it. The important question of how gravitational fields propagate was treated by me in my academy paper 1.5 years ago. However, I have returned to the subject since my former presentation is not sufficiently transparent and furthermore is marred by a regrettable error. It was this paper that became the reference point for the further investigation of gravitational waves, although their existence remained controversial for a very long time to come. So very quickly, how did the story end? The formative years lasted roughly until the early 1930s, when interest in general relativity waned and more of the leading physicists turned their attention to the booming field of quantum mechanics. Then the formative years were followed by a low watermark period when general relativity was considered as basically irrelevant to mainstream physics. And Clifford Will, who is here with us, proposed to call the subsequent period a renaissance of general relativity, which began only after the war with the new astrophysical discoveries in the 1960s, such as that of the quasars. And eventually this turned into a veritable golden age. I think the label is due to Kip Thorne, also in the room, bringing new conceptual insights such as those into the nature of black holes and turning the theory definitely now into the foundation of modern astrophysics and observational cosmology. It was crowned by the discovery of gravitational waves. So let me conclude with a final remark on the Renaissance and the Golden Age, another topic that we are currently investigating. They were not just the result of Cold War technology and funding, as one might assume. They were the result of a community effort exploring the untapped potential of general relativity. Many more people got involved. And that changes the situation for us historians as well. We have to deal with many more people, not just with Einstein's manuscripts. Historical analysis of this period requires new tools of analysis, for instance, social network analysis. Let me give you just one example for the analysis of cooperative relations in general relativity. It shows that the most central actor in the network of collaborations of relativists, in particular between the mid-1960s and 1980, was none other than Kip Thorne, initiator of LIGO. And this is not because he wanted to write Kip's name in capital letters here. This is the outcome of a calculation that my colleague Roberto Lalli has done. In other words, general relativity, from its creation by Einstein to its current advances, was a product of genius. But it also was, to a surprising extent, a community effort. And this also holds for the history of science, of course. I just want to mention my colleague Michel Janssen here once more. I want to single out two institutions and two persons that have made Einstein studies in particular a field of productive collaborative work worldwide. One is the Hebrew University holding the Einstein Archives and its former president Hanoch Gutfreund. The other is the project of the collected papers of Albert Einstein here at Caltech. And its director, Donna Buckwald, a true leader, a magnificent editor, and a reference point for the community of Einstein scholars. She is. With these remarks, I thank you for your patience and for your attention.
Thank you, Jürgen. It was a wonderful talk. I particularly like the ending with that picture of Kip spread in red with all of the connections. We have time for a few questions, so please, if anybody has anything, I'm happy to call on them. Sir. Any further? Good.
Can you repeat the question, please?
Yeah, it was just a comment. It was a comment. It was a comment, Christine. Yeah. I have one. Do you want to say maybe a few more words about the difference between Hilbert and Einstein in respect to their views of mathematics-physics relationships, which you touched on fairly
So when Hilbert entered the theme of general relativity, it was from a perspective of the axiomatization of science. He had a whole research program trying to axiomatize physics. And his first target was the theory of matter that had been proposed by Gustav Mie based on a nonlinear version of Maxwell's electrodynamics. And then he tried to combine this with Einstein's new theory of gravitation. And what he tried to formulate in his paper that was then published in 1916 was an axiomatization of a theory that encompassed both gravitation and electromagnetism from this perspective. And he didn't bother, to go to all these procedures of checking whether something like the perihelion motion could be explained by it and so on and so forth. But eventually, Einstein himself, who initially thought, he even used the word that this was a childish attitude with regard to physics, became fascinated by it because eventually he began to emulate Hilbert in his attempts to create a unified field theory because there were no empirical clues for this unification other than the mathematical beauty. And this, I think, became a temptation to look at his own achievements as having been the result of that search for mathematical beauty and harmony.
Did they ever meet to talk about this?
There is a letter that Einstein wrote, if I remember correctly, to Zanger, where he says only one colleague has actually understood the theory, and that one is trying to nostrify it. That was the expression that Einstein used, to appropriate, to nostrify it. And, but a short while later, they made up for it because they were also allies in their opposition against the First World War, and they had many things in common, and they basically forgot about this conflict. It never became a big issue between them.
Yes, sir. Speak up here.
There are two questions. Back to showing the gravitational wave.
I think, but there may be others in the room who know this episode better than I'm not sure whether Dan is here. For what I remember of the episode is that it was actually Robertson's criticism who made Einstein change his mind about this, and he basically withdrew his conclusions and didn't express himself anymore on gravitational waves. He, of course, had found an interesting exact solutions that he misinterpreted as showing that gravitational waves don't exist. But so he withdrew that conclusion and he pursued this research in a different direction, never dealing with the issue anymore. But there are more details to the story which I...
Kip?
So one thing that Hilbert, even in the final version, did not change, and that bothered Einstein as well, is that he didn't consider a generic energy momentum tensor as the source of the gravitational field. He looked at a very specific one, namely the one that he got from Gustav Mie's nonlinear electrodynamics. So that was the part where he tried to unify. The other element in his theory that he did change from this page proofs version to the final version was a condition that he thought he had to impose on the coordinates. And he calls it an energy condition, although it's not clear why that should be an energy condition. And my interpretation is that this is nothing else but an attempt to emulate the logic of the N-Wolf theory, where all these physical conditions, Newtonian limit, energy momentum conservation, imposed restrictions on the admissible coordinate systems. And so he basically took the physics from Einstein and wrapped it into elegant mathematics without extracting, the new physical semantics that you can get if you really understand the relation between the formalism and the concepts. So, these conditions are completely meaningless, and he just took them out. He introduced them as an axiom in its own right. I forget which number it is, but he has an axiomatic structure, and the restriction on the coordinates is an axiom by itself, which is very strange. Hilbert published the article, as I said, in March 16. Then I think it was at least 2 or 3 times republished in Hilbert's editions, collected works, and so on. And every time he kept the date line, 20th of November 1915, and the contents gradually changed. John Stetcher and myself, we have written a paper on it where we compare all the versions, and you see how gradually he basically repeated the learning experience that Einstein and Grossman had done before him in the Zurich notebook. It's a very interesting story.
Good arguments about how Einstein did his science. It's happened in the community. And the second, if I understood right, that he didn't always know where he was going, that the goalpost shifted. The question is, how exceptional would you say he was, either in his time or in science generally, as a collaborator and as someone who was? Are you simply telling us Einstein was not, born? Or are you saying he was an exception?
Let me come to the first of your arguments first, namely the collaborative nature. I have emphasized that because that seems to contradict the standard image of Einstein as a loner. And there is something to both sides, because as I also tried to show, very few physicists, contemporary physicists, believed that the creation of such a new theory of gravity would be a worthwhile aim to pursue. And the ones with whom Einstein collaborated were less the famous physicists rather than his club of friends from Zurich, his student friends. There was this bonding between peers that, that started with the academy, the famous Academy Olympia, surrounded him in 1905. And that was still active in the period when he created general relativity. And I think it was also important as an emotional support because he was on a lone trajectory there, effectively. So, that has various dimensions. And the second dimension, he was pragmatic, as you can see. He's neither a strict Machian, just thinking in relative motion. He also, served himself of the resources of field theory. So in that sense, he was pragmatic. But I wouldn't agree with the statement that he wasn't strictly goal-oriented. He was not an opportunist as far as his goals. He had set these goals very firmly, very early on, and he was pragmatic in terms of the tools that he was using to follow these goals. And what I think made him special, to come to the bottom line of your argument, was that he had an ability to capture those contradictions in the conceptual systems of his time. When I would think of one thing that characterizes Einstein's mind, scientific mind of this period, was his sensibility for these big clashes of principles. We once made, when this wonderful tool of the digital version of the Einstein papers came out, I had just fun searching for the word contradiction, Widerspruch, in Einstein's early time. And you are amazed how often it appears and how he searches for them and how he knows how to make them productive. That is what impresses me mostly about his scientific persona.
Sure.
Well, if I remember correctly, he wrote a paper in 1939 in which he rejected that black holes could exist. But there again, he was not alone. Many people believed that such singularities had no physical meaning, but were just showing a limit of the theory. And so the physical interpretation of this complicated formalism, including its singularities and the use of coordinates, that was a broad community effort that came to fruition only in the 16 with people like Penrose and others who really established what the physical meaning of these features were. Before, there were pioneering attempts by Oppenheimer and his collaborators, for instance, but it became a safe knowledge of physics only with the period of the Renaissance. That's a good question. No, they were, to my knowledge, they were not peer-reviewed. Basically, the editors decided about them. And that's related to that other question, when Einstein learned from the reviewer of the Physical Review that his paper on gravitational waves wasn't accepted or was criticized, he wrote back, I submitted you this paper in order to publish it, not for you to show it to other colleagues and have it criticized.
First, on that point, if I recall correctly, publishing it in that.
I think so. Diana may know it better than I do.
And Kenneth discovered the whole story.
I'm waiting for his comment. I don't see him.
Yes, he never published again in Physical Review. What those equations?
It was not so much the formalism. It was the underlying structure, that you have a field equation and that you have an equation of motion. And that the field, the appearance of the field may depend on your state of motion. Like the electric field may turn into a magnetic field in dependence on how you move. It's more on this qualitative, analogous way that Einstein used the analogy. Initially, he also thought, what mathematical object can represent the gravitational field? Is it a 6 vector, or what could it be? So he tried also to use the formalism initially, but then he stayed away from using the analogy too literally and used it more as a qualitative, as I call it, a mental model.
Now, maybe I should conclude not only by thanking Jürgen, but also by mentioning that the next 2 days we're going to have a wonderful conference, which is a collaboration between humanities and social sciences and physics, mathematics, astronomy, and the Huntington. Wonderful lecture, and of course it's particularly exciting because of the LIGO success and talks by historians and scientists who are directly involved. Barry Barish, sitting over here, of course, involved in the entire success of the project, and I urge all of you who can to attend. By thanking Jürgen for his wonderful introduction.
Thank you.